Okay, so this is the quiz review session for this energy quiz that we have tomorrow for some professors and I don't know, Thursday I think for other professors. But I don't have any, like I said, I don't have any quiz problems. Unfortunately, we never took a quiz on energy. I don't have access to any sample quiz problems, but what I do have is all these lecture slides and extra practice problems that are hopefully going to be helpful for you guys to better understand concepts of energy and stuff. And then we're going to go over, hopefully, some online homework problems as well. But I'm going to start off with the work energy theorem initially, just to kind of explain what's going on with that concept. And then by doing that, we're going to go over some conservation of energy type problems and very complex problems when it comes to calculating energy and stuff like that. So, without further ado, I think we can get started. So, first of all, hopefully you guys, let me know if you can't see my screen. Hopefully you guys can see it. Okay, we can. Awesome. So, work energy theorem, potential energy. So, with work, right, this equation here was pretty much from the beginning of the lecture slides, and that's the concept that work is equal to the change in energy that you have, right? And for mechanics, right, we're not concerned with heat necessarily, energy transferred by heat. That's something that you're going to be doing in physics 132. And so work is the only way energy is transferred in or out of the system. We're not, normally it would be work plus heat, which is Q. You've probably seen that at the beginning of the lecture. But we're not going to be concerned with Q. We're not going to be concerned with heat. You might have also seen Q with like Q is equal to MC delta T in chemistry, right? Thermodynamics. That's what you're going to be doing in 132. And we're not concerned with that for 131. We're just concerned with mechanics, and that work is the only way energy is transferred in or out of the system, right? So the idea here that makes this equation so important is the fact that there's internalization and externalization of forces that causes this equation to be slightly different depending on how you look at things. So what I mean by internalization of forces versus externalization, if I internalize a force, right, that force is inside of me, right? It's part of the system that's in question, right? So let's say if I'm a person here standing over here, right? Well, normally there's gravity acting on me, right? There's a force of gravity acting downwards, pulling me down to the ground, right? So that force of gravity, let's say if I jumped out of a plane, right, and I'm skydiving, and force of gravity is pulling down on me, then technically I could think of force is doing work on me, right? So if I'm falling downwards, then I can calculate, for example, work is equal to the force of gravity times the distance, right, that work is applied on, or that force is applying work on, right? And then times the angle, cosine theta, at which that force is acting, right? So if I'm falling downwards like this, d, and the force is acting along the exact same direction, force of gravity, cosine is 0, right? So cosine of 0 is 1, so this becomes 1. Then I can calculate force of gravity, right? That would just be my mass times gravity, and I just can calculate the distance at which that force was acted on, right? Or is acting on. So that's how I can calculate work due to gravity if gravity was external to my system, right? So gravity is outside. So if I were to draw a free body diagram of myself, it would just be this point right here, and gravity pulling me downward, and then assuming that we're going to ignore like air resistance and drag or anything like that, force of gravity would be the only thing acting on me, pulling me downwards, doing work external to my system. So you can see here a really nice way to think about internalization versus externalization is think about this circle here. This circle here, right, represents any of my forces, my energies, everything that's internal, everything that's wholesome to me, right? So when I externalize the force of gravity, it becomes external. You can see I can see or draw a line outside of that circle representing force of gravity. When I externalize that force, when that force is external to my circle, when it's external to my wholesomeness, I guess, right, then I can calculate work due to gravity. However, once I externalize a force, Once I externalize it, then I can no longer calculate for certain energies. So in terms of the force of gravity, if I externalize the force of gravity, it's outside of my circle. Yes, I can calculate for work. I can do Fg d cosine theta, but it disables me from being able to calculate the change in potential energy, specifically gravitational potential energy, right? So when I'm writing my work equals change in energy equation, if I externalize a force of gravity, for example, then I can say, okay, well, work due to gravity is going to equal the change in energy, and that's going to be equal to my change in kinetic, right? So in this case, I can think about, well, okay, what does this mean? So it just means that there's going to be a change in energy, right? So once I jump out of that plane, I might have started out at rest, and now I'm falling down, through the air. So when I'm falling, there's acceleration due to gravity, for example. So I'm going to be speeding up. I might go from 0 meters per second to 20 to 30 to 40 to 50, right? I'm falling down faster and faster and faster and faster and faster, right? So if I look at my change in kinetic energy, knowing the idea that kinetic energy is equal to half mv squared, well, as I fall through the air, right? Well, this v is going to increase and increase and increase and increase, right? It's going to keep increasing up until a terminal speed, theoretically, but, it's going to keep increasing. So there's going to be maybe an increase in kinetic energy, for example, right? Now, once again, when we look at this equation, because I externalize gravity, now that gravity is a force external to the system, then when it's external, I can no longer calculate for this, what would be UG here. When I externalize the force of gravity, I can no longer calculate for gravitational potential energy, right? So then I'd have to look at, okay, well, what's the work due to gravity? That work is going to be causing a change in energy, right? And that makes sense. Why? Because let's say that force of gravity is doing work equal to, 70 Newton meters, right? So it caused a change, and that's, so in meters, that's joules as well, right? 70 joules, let's say joules, keep it easier. So it caused a work equal to 70 joules, right? So there was a change in energy equal to 70 joules, for example. Change in energy of 70 joules. Well, that's going to be equal to the change in kinetic energy that I observed, which is going to translate to that change in speed. So if I went from 0 meters per second to like 20 meters per second, that might have caused a 70 joule increase, right? A change of energy of 70 joules, maybe a positive 70 joule change in energy due to the work that gravity did, right? So gravity is external to the system in this case. This is the external perspective, where gravity or other forces, for example, are going to be acting external outside of this little circle here, right? When they're external, they're outside of the circle. And so they'd be doing work on the system. And then the issue here is that once I externalize that force, and that force is going to be doing work on the system, I can no longer calculate for the gravitational potential energy changes, right? Whatever work is done due to gravity externally is going to equal the change in energy that it causes to my system. And that change in energy is then only equal to kinetic energy. Because like I said, when I externalize gravity, I can no longer calculate for UG. Now, if I were to internalize gravity, if gravity were to be part of my system, right? If gravity is internal, then I'm not concerned about what work or forces are, acting on me. So if I were to redraw my free body diagram, it literally looked like a dot. Inside of this, and if we were to expand this, right, if we were to look inside this dot, if we were to look inside the circle here, we can see that once we internalize it, we can think about what's inside the circle. Oh, what's inside is the kinetic energy and the gravitational potential energy. It's internal now. So this is internal. And if it was external, so this is internal. If it was external, it'd look like this. So it'd be kinetic. And then here's the force of gravity external, outside. It's drawn outside of the system. When I internalize it, when I internalize the force of gravity, it's inside the circle. Therefore, I can calculate for UG. If it's external to the system, force of gravity is on the outside, it's doing work on the system, therefore I can't calculate for UG anymore if it's external. Okay, so going back to this idea of internalization, once I internalize force of gravity, I can calculate now for gravitational potential energy. And what that means is, given that there's no air resistance, no friction, no any of that, no other forces acting on me, right? Then I can say that, okay, well, there appears to be nothing else doing work on you, so work is zero, right? Because you've internalized everything else. You've internalized the kinetic, you've internalized gravitational potential energy. There are no other forces acting or doing any work on you, so work is zero. There's no work being done. So in that case, once again, W is equal to delta E. So if W is equal to delta E and the work being done is zero, well, then your change in energy is zero, right? And once again, like we said, well, change in energy is a sum of all the different types of energies that you have. And since we've internalized gravity, we can now successfully calculate for both kinetic energy and gravitational potential energy. So this becomes part of the equation now. Now you can see here that since this is part of the equation, right, I started maybe, let's say for that plane example like before, if I had jumped out of the plane at a height of, 3,000 feet, right? I have a certain potential energy. As soon as I drop out of the plane, well, my altitude is going to be decreasing, right? I'm going to go from 3,000 feet to 2,900 to 2,800 to 2,000, right? Then, based on the idea that mgh is equal to ug, my height is decreasing. There's a decrease in my gravitational potential energy, and there's a subsequent increase in my kinetic energy, right? Because if I start from rest 0 meters per second, and I fall through the air, we can think about it logically, I'm going to speed up, right? As I fall through the air, I'm going to be speeding up. So whatever decrease that I see in gravitational potential energy due to a decrease in altitude or a decrease in height, I'm going to see an equal increase in kinetic energy, right? And so that little relationship there, that whatever decrease I see here is going to equal an increase here, is kind of like a push and pull kind of relationship. Whatever power gets sucked out of gravitational potential energy is the power that's sucked into kinetic energy, right? It's very informal, but that's the kind of the way to think about it. And so since there's no work being done, there's no other external forces in this situation, right? We're assuming that there's no drag, there's no air resistance, there's no nothing. So work is equal to zero in this case, right? If work is equal to zero, then your change in energy is zero. Therefore, we can say if your change in energy is zero, then if your final and the initial are the same, there's no change in energy, then energy is being conserved. And so if energy is being conserved, right, then if this was an increase in 30 joules, then this was a decrease in 30 joules. So energy gets converted from, 30 joules of, let's say if you started out 30 joules of potential and zero kinetic because you started from rest, right? And then all of a sudden you jump out of the plane, your altitude starts to decrease, so maybe you went to 20 joules now of gravitational potential energy, right? Then you have that 10 joules now that have been transferred over to kinetic, right? Still, it helps you equal that 30 initial, right? So there's no change there from your initial starting energy. Everything is conserved, right? So if I went from 30 to 20, right, joules of gravitational potential energy, I experienced a decrease, right? So it would be minus 10 joules. At the same time, those 10 joules that went from, I went from 30 joules of gravitational potential energy to 20, those 10 joules were converted into kinetic, right? So I have an increase of 10 joules for kinetic. So that equals a 0 joule change, right? I don't have any change in energy here. So that makes sense once again, because if I internalize everything, there's no work being done on the system. So I have a work equal to 0, energy is conserved. The thing is regardless if you internalize or externalize energy, or internalize or externalize forces, and then therefore internalize or externalize energy, you're still going to observe conservation of energy. Conservation of energy, once again, like the conservation of mass, right, is the idea that energy cannot be created or destroyed. So whether I internalize or externalize energy and forces, it doesn't matter. Energy is still conserved. It's the idea that now, how am I calculating for this stuff, right? So if there's work that's being done, right, like we said before, if gravity was external and there's work being done, then that work is going to detract energy from the system. Can we account for it? Yes, we can, right? Can we calculate for it? Yes, we can. So if we started off with 30 joules, right? And then we decreased, this was our initial, right? And our final was 20 joules, for example, right? There was 10 joules lost. Well, that change in energy would be negative 10 joules, right? And that would be equal to the work done by gravity, for example. So if we were to add, let's say if we were to add the joules lost from gravity back to our final, so if this is when we're at the ground, right? Let's say this was like joules are tangible, right? Let's say if it was money or something, or if it was, I don't know, like your parachute, right? And your parachute, I don't know, got cut off or whatever, right? When you're doing skydiving. So if we were to add back those 10 joules lost, right? If it's something tangible, then we can get 20 plus 10 and we still end up with the original amount. Was it lost? Yes, technically, right? It's lost or detracted from the system. However, we can still account for it, we can still calculate for it, and if we add everything back together, we're going to end up with the initial energy. So despite observing a final energy that's different from our initial when work is being done external to the system, if we legit just add back the work, right? If we were to add back this loss of energy to the final position, we get our initial amount of energy back. Energy is still conserved in either case, but theoretically, or at least when we're doing the math, whatever work is being done external to the system is quote unquote lost. It's not destroyed, it's just lost, it's missing, right? So if we, I don't know, like if you were running a race, right? And let's say you have a really heavy jacket on, right? If you have that heavy jacket on you, then maybe it's pulling you back, it's doing some work on you that's preventing you from going really fast, or it might be slowing you down, right? So if you started off the race with 60 joules and you ended up with 20, for example, and by the end of the race, let's say you found that you're no longer wearing the jacket fell off somewhere along the line, right? Well, then I ended up with 20 joules, that's a decrease in my energy. Maybe if I go back and find the jacket somewhere along the race, I can find that 40 joules that I lost, right? So the 40 joules I can still account for, but it's quote unquote lost energy. I ended up with lower energy than I started with, but I can still account for everything because energy is not created or destroyed. But in terms of initial and final position, if work is external to the system, in terms of initial and final position, then you experience a loss of energy, quote unquote, right? But if everything is internal, if gravity is internal, friction is internal, for example, if all that's internal, then you experience zero work, your change in energy is zero. So energy is still conserved, but now it's like, in terms of our calculations, we can see that it actually is conserved in our calculations. So if we went back to that running example, right? If you started off with 60, you end up with 60. But the thing is, if that friction was holding you back, exerting work on you, it might have been thermal energy, right? And so that thermal energy is going to be internal to you as opposed to external. We can say that the jacket, for example, the jacket is exerting some kind of friction force, right? The jacket might be exerting friction force, right? That friction force, we can either externalize it or internalize it. If we were externalizing it, we would calculate for work due to that friction. If we were to internalize it, we'd calculate for thermal energy. If you internalize it, right? If you were to internalize that friction due to the jacket, then you see that if you were to calculate for your delta E, you know that work is equal to 0 because you've internalized the friction. And then that equals K plus U plus thermal energy, right? That's if you internalize everything. If you externalize it, then work is done by the jacket, and that causes a loss in energy per se, quote unquote, a loss of energy. And then that is equal to K plus U, right? So you can see here that the work done by the friction from the jacket is the same as the thermal energy. It just depends on if I internalize or externalize that concept. If I internalize everything, work is 0, energy is conserved in terms of my calculations here, and I calculate for thermal energy on this side here. Thermal energy is going to be the same as the work done. The idea here is that if I externalize it, I can't say that there's a thermal energy. I just have to say that there's work done by the jacket on me, that might be slowing me down, for example. Right? If the jacket's really heavy, you might go slower than you would. So there might be a decrease of 20 joules, for example. So if you started off, like I said, if you start off 60 and you'd end up with 20, there's a loss, there's a minus 40 joule loss. That's equal to your delta E. So that means that the jacket did 40 joules of work on you. It detracted 40 joules. It subtracted 40 joules from you, right? So there's quote unquote a loss of 40 joules. Does that mean that the energy was destroyed? No, it just means that energy is still conserved. It's just that your initial and your final positions, right? Your initial and final energy is going to be different, but we can still account for everything. So if that jacket, right, acted on you externally, and you ended up with a different final energy, EF is different than E initial, then if we can say that jacket might have been external, and so that jacket external, we can say that jacket might have fell off of you somewhere during the race. So if we look for a jacket somewhere in the middle of the race, right, we can pick up that jacket and we can be like, okay, well, that jacket was, here's the 40 joules that you were missing. We can add it back to your initial, and we can be like, okay, well, you plus the jacket that was external to you is 60 joules now. So here's your 40 joules back, right? As opposed to if that jacket was like sewn onto you, now it's internal, right? If the jacket, as opposed to you wearing it, it was sewn on, for example, right? If it's just part of you, it's internal, it's part of your system. So then your initial end up being the same as your final. 60 joules and 60 joules. In both cases, the jacket is technically doing work on you, right? You might feel a little bit hotter, you might slow down a bit, your kinetic energy changes, but instead of calculating for that friction force, what work it does, we can't say it's work anymore. If we internalize it, we say that it's thermal energy now. So that's the idea of internalizing versus externalizing forces and energies. Now, here's a question in the chat. Is there ever a question where UG is internalized and there's free fall, like what happens when you reach terminal velocity? So for gravitational potential energy, you can very well, in fact, it's probably easier to internalize it most of the time. And you can internalize it if you wanted to, if you're doing free fall. And that's just a matter of what? If you internalize gravity, like we had here, then you no longer have a force of gravity acting externally to you. And so now you can say work is 0. That means there's no change in energy. And then K plus U is how you can calculate for changes in gravitational potential energy, for example, and how you can figure out maybe your final speed or something like that, right? And so internalizing allows you to calculate for gravitational potential energy. If I were to externalize gravity, I can no longer calculate for gravitational potential energy. I'd have to calculate for the work done to gravity. And since in this case, the angle is easy to find out, right? Because if you're moving downwards like this, D, and your force of gravity is acting in the same direction, directly in the same direction, then you can do FG, D, cosine theta, and you're good, right? Either way would work. However, if you did one of those like loop-de-loop problems or one of those more complex problems, right, it'd be really difficult to externalize gravity because the angle is going to be different each time. So it's almost always better to internalize gravity as opposed to externalizing it. But where you're gonna see internalization versus externalization, for example, of forces, is especially with this concept of thermal energy here, which I just explained. So whether you internalize or externalize forces and energy is still conserved. Energy, law of conservation of energy is not created and it's not destroyed. When we say it's external, right? When we say force is external, and so energy is external, right? Then in that case, you have work done, work is done. And so when work is done, it might decrease, for example, or it might increase your energy, right? Because work is equal to the change in energy. If work is being done, you might see an increase of 30 joules, for example, or a decrease in 30 joules. But the idea here is that, you might see an increase of 30 joules or a decrease in 30 joules, and we can still account for that, right? You might think that, 30 joules, there's an increase in energy. Then energy is created. No, it isn't, right? It's just the idea that energy is still conserved. It's just that if we're doing work, there might be energy lost or added to the system, for example, but everything kind of equals each other in the end. And so usually you'll see like a decrease in work. So there might be a decrease of 30 joules, right? That might be due to friction, for example. So if friction is doing 30 joules of work on you, then there's a decrease in energy. And that decrease, then, is going to be equal to the sum of your energies. So you might have kinetic, you might have potential, and you also, actually, no, you wouldn't. Yeah, you would just have kinetic and potential. That's if you externalize the work due to friction, for example. If you were to internalize it, then no work is being done, right? There is no change in energy, but then, well, that friction force is still in play, right? It has to exist. It would just be now equal to K plus U plus the thermal energy. So E thermal is exactly the same value as work due to friction, right? The idea here is internalization versus externalization. If it's external, there's work. If it's internal, it's called thermal energy. External is work, internal is thermal energy. In both cases, energy is conserved. It's just that when things are external to the system, we can quote unquote say that they're lost from the system. Energy is lost, or energy might be added to the system, for example. But we can account for and add for all these different changes. But if you internalize things, then you're like, okay, well, I don't see any external forces acting on me, right? There are no external forces necessarily acting on me. I'm not accounting for any external forces. So whatever I ended up with is the same as what I started with. And so in that case, there's no change in energy that you can see from the equation itself. So that's the concept of internalization versus externalization of energy and forces. Does that make more sense, hopefully? Any questions about internalization versus externalization at all? Because you can see here as well, this bottom part, is that for any mechanical system, not changing the thermal energy, friction is external to the system. So this would be an example of an equation where friction would be external, for example. There would be work done by friction that we can calculate. We can say force of friction times d times cosine theta, and that equals the change that you see in kinetic energy plus the gravitational potential energy. Otherwise, if we're internalizing friction, then this work goes to zero. There are no other external forces, so there's no change in the energy. Energy is completely conserved, and we can see that because delta E is equal to zero, so energy is conserved from the perspective of the equation itself. And then that equals K plus U plus the thermal energy now. So instead of calculating for work, right, due to friction on the left, we do it on the right hand of the equation. We just refer to it as thermal energy instead. Make sense? Because then we're going to get to a very difficult problem here to kind of explain this stuff a little bit better. You guys ready to move on to the problem, or anybody still confused about the internalization versus externalization of stuff? And Christian, does that make sense about the free fall stuff that you asked about earlier? Yes, no, maybe so. You guys can hear me, right? I just want to make sure because like y'all are dead silent today. Oh, Christian left? Okay. All right. No worries. All right. Well, I guess if you guys don't have any questions about this internalization versus externalization concept, we can move on to the problem here. So this problem is pulling a bike trailer. Did you guys have this problem on your slideshow or not? Monica pulls her daughter Jessie in a bike trailer? Nope. Okay, excellent. Alrighty. So here, Monica pulls her daughter Jessie in a bike trailer. Trailer and Jessie together have a mass of 25 kilograms. So Jessie and the trailer have a mass of 25 kilograms, right? Now, it says Monica starts up a 100-meter long slope that's 4 meters high. On the slope, Monica's bike pulls on the trailer with a constant force of 8 newtons. So we have a height here equal to 4 newtons, or 4 meters. And then the length of the slope itself is 100 meters. Now, it says they start out at the bottom of the slope with a speed of 5.3 meters per second. So we can say that VI is 5.3 meters per second, right? And then what is their speed at the top of the slope, right? We want to figure out what VF is in it, essentially. And it says to ignore rolling friction and any forces from the air. So no air resistance, no rolling friction due to the trailer or the bike or any of that, right? And now it says, hint, first make a good choice for the system, then use work energy theorem, right? Now, the issue with this problem refers once again to the idea of internalization versus externalization. We have Monica on her bike pulling the trailer, right? Monica and bike pulling on the trailer, right? And then we have Jessie and the trailer itself. Jessie and the trailer itself, right? So Monica pulls on the trailer with a constant force of 8 newtons, right? So if we think about what, this is like a free body diagram, right? This is our circle. This is Jessie and the trailer. Then Jessie and the trailer feel a 8 Newton force. You think about that maybe kind of like as a tension force and something like that, right? Or maybe a F pull force would be better, right? This is pulls on the trailer with a constant force of 8 newtons. So Jessie and the trailer together feel an 8 Newton force pulling them up and to the right on the slope here. Well, that's not a, I was going for a triangle, not a circle, right? So they're going up and to the right, basically, on that slope. And so they feel that 8 Newton force pulling them up and to the right along that 100-meter long slope and up that 4 meters slope, right? It's 4 meters high. Now, Monica and the bike, right? Actually, before I go Monica and the bike, we have this 8 Newton force. That's external, right? We can't really, there's no way of internalizing it for us because it's not like friction. It's not a thermal energy, right? It's not, gravity, right? So we just call this an F pull. So this F pull is doing work. So we have to include work in this case, right? Work is relevant, right? So theoretically, we can say that, okay, well, maybe work is being done on the system, right? So work might be added or work might be removed from the system, whatever. But in general, energy is conserved, but we're just accounting for or calculating for that work done on the system, right? In this case, since we're moving up and to the right, and she's pulling, Monica and the bike are pulling up and to the right as well with that F pull force, it's in the same direction, so work is positive. So work technically is like being added to the system, basically, right? So that's what Jessie and the trailer are feeling in terms of external. Internally, right, what things can we internalize? So if it's Jessie and the trailer, and we know that their mass combined is 25 kilograms, right? What can we internalize with relative to Jessie and the trailer in terms of energies and stuff and forces and all that? Kinetic energy and gravitational potential energy, right? Yeah, exactly, UG. Because we can internalize here, we can internalize UG and we can internalize kinetic energy, right? And then the only thing that's external would be that F pull that's doing work, right? You might think, well, okay, well, why can't we externalize gravity, for example? Well, if you think about it, if here is Jessie and the trailer, force of gravity always points downwards, right? Here's the movement of the bike and the trailer and Jessie, right? They're moving up and to the right on the slope, this way. So here's the angle. Do we know that angle? Hell no. There's no way for us to calculate that, right? So there was no way we can externalize gravity in that case. So it's far better to internalize it because we don't have access to an angle or anything like that. So we internalize gravity, so that allows us to calculate for gravitational potential energy. and we internalize kinetic energy, obviously, right? So because we have an initial speed, we have a final speed that we want to calculate, and we have an initial height, which is at 0 meters at the bottom of the slope, and we have a final height at 4 meters at the top of the slope, right? So we can easily calculate for gravitational potential energy and for kinetic energy if we internalize both of those. And then the only thing that's external would be 8 newtons, that F pull force, which is easy. So we can calculate the work. Remember, work is equal to change in energy, and that's equal to kinetic plus potential, right? We can figure out what the work is here. That's the F pull force, right? And since work is positive because the distance and the force direction are the same, then there's going to be an increase in energy, for example. Doesn't mean that energy is created per se, it's just that means that we can calculate for a force that's doing work, and that work is being added to the system, and then in general, like everything kind of cancels each other out and stuff. So that is actually one of the systems that you can use, theoretically, Jesse and the trailer. If we look at Monica and the bike, what's the issue with Monica and the bike? The issue here is that they're being pulled backwards, right, essentially, by the trailer. Let's say that was, the same 8 newtons, right, pulling backwards. Means think of that 8 newton force almost, like I said, or we can almost think of it as a tension, for example. So they're being pulled back with some force, right, that would be doing work external to the system. Sure, that makes sense, no problem. But the issue here is that there's also another external force. What is that? Static friction. Why? Because remember, she's on a bike. And that bike really is the key in this whole problem, right? The bike is the one that's like driving them upwards, that's propelling them forward together as a system, right? All of them, Monica and the bike and the trailer and Jesse. What's doing like the brunt of the work is the static friction force from the bike, right? That's helping propel them forward up the slope. There's no way for us to figure out what this static friction force is. This static friction force, right? If they were to say if it was Fs max, we can say, oh, mu times Fn. Well, we don't have mu, so we can't do that, right? And the normal force, we know that normal force is perpendicular to the slope here, right? And so here's force of gravity, and we know that Fgy, for example, might be equal to the normal force. Well, we don't know what the force of gravity is for Monica and the bike because we don't have the masses for them. So regardless if we internalize or externalize gravity or static friction force for Monica and the bike, we just don't have enough information to consider Monica and the bike as a valid system, right? Because we don't have masses for Monica and the bike, and we don't have any information about static friction force from that bike that we can use to either internalize or externalize friction and then figure out the final speed. Because remember, our issue here is that we're trying to figure out the final speed at the top. So let's say even if we wanted to internalize gravity, right? If we were to internalize gravity, internalize kinetic friction, and externalize static friction force, well then work is equal to change in energy, right? And this is work due to static friction force, by the way. And then this is equal to K plus U, right? Well, we don't know the mg part of U, right? We don't know what her mass is, or the mass of Monica and the bike. So we can't really calculate even for gravitational potential energy, right? Same thing if we externalize it. If gravity is external, right? We don't even have the mass, and nor do we have that angle that would be required to figure out what the force, what the work done by gravity is, right? So this whole system here with Monica and the bike is just invalid because it's just impossible for us. We don't have enough information to calculate static friction force or the force due to gravity. We don't have masses. We don't have nothing, right? So it's just easier if we use Jesse and the trailer as our system because we have the masses for them, so we can internalize gravity and kinetic energy, and we have this external pull force that we can calculate the work for that's being added to the system, right? That's where this stuff comes into play. So we know that there's work being done by Monica and the bike on Jesse and the trailer as a system that's pulling them up and to the right on that slope. So there's going to be a change in energy because there's work being done. In terms of the equation itself, right, there's energy being added to the system, right? Now, how much is that energy? Well, they said she's pulling with a constant force of 8 newtons on the trailer and Jesse, and that's along a 100-meter long slope. And obviously it's in the same direction. Direction is the same as the force that she's pulling in. So cosine would be 0. So you take 8 newtons times 100 meters. That gives you 800 newtons. 800 newton meters, or 800 joules in that case. And then you have your change in kinetic and your change in gravity. Your change in gravitational potential energy, right? So this would be how you do it with the deltas, right? Remember last session I had a horrible time with figuring out or making sure I had the right notations for all this stuff. So if you're not comfortable doing the delta K plus delta UG and doing like KF minus KI plus UF minus UI, right? That's just, I would forget about the delta stuff, and I would do instead work is equal to delta E, right? And that's equal to, work is equal to delta E, and that's equal to EF minus EI, right? So that way you can say, well, work is equal to EF minus EI. Work plus EI is equal to EF, right? That way you can just add your initial energies, right, to work, and then that'll be equal to your final energies, right? And so the idea here, and I'll move on because this is far better organized here, is that you can see here what I was talking about. Work plus your initial energies, these are your initial energies here, is equal to your final energies. These are your final energies here, right? And so when you're looking at energy initial or energy final, it just means that I'm looking at all the different types of energies that are in play at different points. So if I were to think about that bottom of the slope, do I have an initial gravitational potential energy? At the bottom of the slope? If we were to make that our 0 point, theoretically, do we have a gravitational potential energy in that case? Yes, no? I mean, if you're not sure, that's totally fine as well. Since we're making this our arbitrary 0 point, right? H is 0. So mgh, our initial height, is 0. So we don't have an initial. It's right here, right? Ui is equal to 0. But we do have an initial kinetic. Why? Because they said you were initially traveling at a speed of 5.3 meters per second. They start at the bottom of the slope with a speed of 5.3 meters per second. So we can calculate for an initial kinetic energy, half mvi squared. We can plug in vi as 5.3 meters per second. We have the mass of Jesse and the trailer, which is 25 kilograms. And then the work is obviously that 800 joules that we calculated earlier, which is the force that they're being pulled with by Monica and the bike, times the distance at which that force is applied, right, times the angle, which is cosine 0. So we add the work there to that system. And then that's equal to our final energies, final kinetic and a final potential. So final potential at that top of the slope be mghf. Our final height is 4 meters at the top of the slope. We have gravity. We have the mass of Jesse and the trailer, right? So we can calculate mghf for uf here. And for kf, well, we're trying to figure out what vf is. We're trying to figure out our final speed. So we have mvf squared. We have the mass, which is 25 kilograms. And we have the final speed, right? That's what we're trying to figure out. We can calculate for that. And we can solve, right? You can see here that I set everything equal to half mvf squared. I solve for vf and I can get 3.5 meters per second, right? So that's a good example problem in terms of trying to figure out how to internalize or externalize certain forces and energies, right? Now, once again, this is conservation of energy, idea of conservation of energy here. Like I said, energy cannot be created or destroyed, it's only transferred, right? Energy is transferred by a force to a system as work, right? So in that case, like if I'm pulling on Jesse and the trailer, I'm adding work to the system. I'm transferring energy from maybe Monica and the bike to Jesse and the trailer. So in that case, everything still can be accounted for and calculated. Energy is conserved. It's not created or destroyed. Energy is just transferred, right? And so that energy is made up of if we internalize everything, kinetic plus potential, and then let's say if there was friction on that slope, then thermal energy, for example, if we were to internalize everything. If we externalized like we had to because there was an external pull force, then we can say that work is equal to a change in energy that's going to be imparted on the system, and that's equal to K plus U, right? That work was the work due to the pull force that's adding energy to the system, and that change is going to be equal to K plus U, right? So that's the idea there. With conservation of energy. So, and then like I said, we don't worry about Q. That's heat energy, right? You're going to be doing that in 132, so I wouldn't worry about it at all right now. So, once again, energy cannot be created or destroyed, only be transferred. So for an isolated system, this is what I was talking about earlier too. Like if you're isolating your system, you're making it whole, you're not having any external forces acting on it, then energy is constant, work is equal to 0, delta is equal to 0, right? So energy is conserved in the sense of that equation right there. It's an isolated system. There's no other external forces acting on it. Everything is internalized. So there's no change in energy because there's no work being done externally to the system. So in that case, like whatever, for example, if I did that skydiving experiment or skydiving problem again, right? Whatever increase or whatever decrease I see in gravitational potential energy due to a decreasing altitude, then I see an equal but opposite, right? I see an equal increase then in kinetic energy. So if I decrease 20 joules from gravitational, it gets transferred into an increase in 20 joules for kinetic, right? When I have that isolated idea of an isolated system where energy is conserved, no work is being done, no other external forces, nothing's doing work, right? Delta E is equal to 0. In that sense, that's when you have an isolated system. That's when you would use W is equal to 0 is equal to delta E. And so any increase or decrease that you see in either, some different energies, you're going to see equal. So if you increase one, the other one's going to decrease by the same amount. If you decrease one, the other one's going to increase by the same amount. But yeah, let's see here. I can do this example real quick. So it says a block with a mass of 2 kilograms attached to a spring is pulled so that it's extended 10 centimeters from its equilibrium position and let go. How fast will the block be moving when it reaches its equilibrium position? Assume friction is negligible, right? So we're not factoring in friction in this case. So there's no work done to friction or work done by friction, and there's no thermal energy, for example, if we were to internalize friction, right? All we know is that there's this block, right? It's being extended, or the spring is being extended, right? 10 centimeters from the equilibrium position. And then we want to figure out how fast the block will be moving when it reaches its equilibrium position, right? So in this case, essentially we're trying to figure out like a final speed, right? A final speed versus an initial speed and a final spring potential energy versus an initial spring potential energy, right? So considering that there's no friction, right? There are no external forces. And if we internalize the spring force here, because there is a spring force, right? If I'm pulling to the right, remember the idea of the spring force is that it's a restoring force. So technically the spring force, like if you were to let go, if you pulled this way, if you let go, the spring force is going to want to bring back the spring that way, right? So you can theoretically calculate for the work done by the spring, but remember, the spring force is not constant, right? Because the spring force is equal to kx. If that x is constantly changing because you go from 10 centimeters to 9 to 8, well, that x changes, so the force changes. So we can't calculate for spring force. We cannot make spring force external because the spring force is constantly changing. If it's constantly changing, the spring force is not constant, right? And so we can't calculate for the spring force's work done on, so the spring force's work done on the block, right, or anything like that, because it's constantly changing. So we want to internalize the spring force. Same way as we internalize gravity, right? So if internalizing gravity allows you to calculate for gravitational potential energy, internalizing, if we have this circle, right, if we internalize spring potential energy and kinetic energy, right? Or internalizing spring force, that's what I meant. Internalizing spring force allows you to calculate for spring potential energy. Same way as if you were to internalize gravity force, then you are able to calculate for gravitational potential energy. So, if we're internalizing spring force, there's no friction or anything acting on it, right? Then energy is conserved. It's an isolated system. There are no other external forces. 0 is equal to delta E. There's no change in energy. Nothing's being added or detracted or subtracted from the system, right? So W is equal to 0 equals to delta E. That's equal to EF minus EI, right? So EF is equal to EI. So your final energies are equal to your initial energies. So you have KF plus UF is equal to KI plus UI, right? So we want to find out what the speed when the block reaches its equilibrium position, right? So if this is 10 centimeters, for example, and I let this thing go, it's going to move back to the left, back to its original position. Let's say its original position, its equilibrium position was right here, right? So that thing isn't going to go here and then stop, right? It might go like all the way inwards almost and then kind of move back, and then kind of like an accordion, right? Or basically just like a spring, right? If you were to let it go, it's going to take a bit to kind of, equilibrate, right? So it's not going to immediately move back to its original position, and it'll just going to go back and forth, kind of oscillate until it kind of settles onto its original position. But the idea here is that we're trying to figure out when it reaches its original position, what's its speed at that point. So we're trying to figure out the final speed at that final position or that equilibrium position, right? So that's our KF that we're trying to figure out. How about our UF? Why is our UF 0? Why is our final spring potential energy 0? Any ideas? Actually, our final is because our spring would be at an equilibrium position. Because remember, what is it? Yeah, spring potential energy is half kx squared. If you're at your equilibrium position, x is equal to 0, right? So if x is equal to 0, then us is equal to 0. So when you're at your final, right, position, our final, we refer to that as our equilibrium. That's where we want to find the speed at, right? Then our final position here is where we have our final spring potential energy. That would be 0 because you're back at the equilibrium position. Does that make sense? Cool. Now with our initial kinetic energy as well, you can see here that the spring is being pulled, it's extended, but there's no motion to the spring yet. So it's like, imagine if you just have it cocked in a position, right, and you're waiting to let go. It's not moving, so you wouldn't have any speed initially, right? So Ki is equal to 0. You do, however, have initial spring potential energy because Us is equal to half kx squared. If you extended it 10 centimeters beyond its equilibrium position, you gave it a displacement of 10 centimeters or 0.10 meters. So you take half times the spring constant, K, times the displacement squared, right? Spring constant is 100 Newton meters. And then calculate for initial spring potential energy, and you can solve for your final speed there, right? So this is another example of internalizing everything because, yes, there's a spring force that's acting on the block, but since the spring force is not constant, because, yes, the spring constant is constant, it's always 100 Newton per meter, the x is not constant because you go from 10 centimeters to 9 to 8 to 7 to 6, right? Whatever. So it's not a constant force. Since it's not a constant force, right, we can't account for all of its changes. We can't, like if we wanted to externalize spring force, we'd have to calculate for the work due to spring force. And if that force isn't constant, we'd literally have to like keep calculating, well, what's FSP d cosine theta when FSP is 10 newtons, for example, instead of 9 or 8 whenever the distance changes. So because the displacement is not constant, the spring force is not constant, therefore we can't calculate for the work for that. So we internalize it to avoid having that issue. This is another example of why you would want to internalize certain forces. Just makes things easier It limits the issues that you have with calculating forces that are not constant, or looking at forces that might be a little hard to figure out the energies for, the work for, because you don't have like a proper angle, for example, or other relevant information. But yeah, and here once again, idea of conservation of energy. One, like I said, in an isolated system, you have W equals 0. Change in energy is 0. Work is 0. There are no external forces. So in that case, even if you were to have a system, right, that would have friction, that friction force, yes, it's doing work. But if we internalize friction force, then we can say that, okay, well, that friction force still doing work, but quote unquote internally. And so when we refer to like an internal work being done by friction, we refer to it as thermal energy. Think thermal, right? Like heat, like warmth. So if you rub your hands together, you can feel warmth and heat, right? There's friction in between your hands there. So instead of calling it work per se, due to friction, and having an external force, if we want to internalize everything and have an isolated system where there are no external forces, work is equal to 0, then that same work due to friction, right, is then equal to thermal energy. We just refer to it as thermal energy. And so instead of saying work is equal, work due to friction is equal to change in energy, and that's equal to delta K plus delta U, right? And then we'd have to do F d cosine theta for here. Instead of saying that, we can say, okay, we want to internalize it, right? So work is equal to 0, right, is equal to delta E. But instead of factoring in the work due to friction on the left-hand side of the equation, we literally just move it over here. We say delta E is equal to K plus U, and then plus the thermal energy lost, for example, right? So when we internalize friction, we refer to it as thermal energy. We externalize it, we just work, right? Because if you internalize things, and if you have no external forces, it's an isolated system, work is equal to 0, right? Let's see here. I'm gonna look at here. And this is another. I don't know if do you guys have this slide as well, or do you guys not have this slide? Nope. Okay. So this is another idea of choosing an isolated system here once again. Like I said, this is probably one of the most important concepts to understand with regards to work. So you choose the ball and the earth as a system, so the forces between them are internal forces, right? So you're internalizing the force of gravity. That allows you to calculate for gravitational potential energy. There are no external forces to do work, so the system is isolated. Here, if you have an object sliding down a frictionless ramp, external force that the ramp exerts on the object is perpendicular to the motion. So if the motion is like this, force is like that, right? You form a 90-degree angle. There's no work being done to normal force, right? And you might say, okay, well, I have a gravity here. But that gravity here, let's say if they didn't give you the angle, right? They didn't give you the angle, then it's just annoying to calculate for the work done by gravity in that case. So it's just better to internalize gravity, so you can calculate for gravitational potential energy, and calculate for kinetic energy as well, right? And obviously, since normal force is perpendicular to the motion, right? It would be cosine 90 in that case. This is 0, and so F d cosine 90, regardless of what the normal force is and what the distance is, this whole thing goes to 0. So when you internalize gravity in that case as well, right, you can figure out maybe the speed, figure out the gravitational potential energy final or initial or whatever, and you also don't have to worry about the work being done by normal force because it's perpendicular. So perpendicular does no work. Object and the earth together form an isolated system. Isolated system, W equals 0 equals delta E. There's no change in energy, and that's going to be sum of your kinetic plus your gravitational potential energy. And so it's frictionless as well. So if there was friction, for example, and it's an isolated system, we want to make friction internal, we can say plus E thermal, for example. If we wanted to make friction external, they can say that, okay, then work due to friction is equal to the change in energy, right? And that's equal to the sum of K plus delta U. So instead of having plus thermal energy on the right, we'll just have work, and that's equal to the change in energy on the left, right? So that's the idea there. And And once again, remember what I was talking about the spring, right? We choose the object and the spring to be the system, right? Because, once again, you should internalize spring force so it doesn't show up as work. Spring force is not constant, so it can't do FD cosine theta. The spring force is equal to K times X. The X is constantly changing because you're changing that displacement. So if the force is not constant, then you can't really properly be able to calculate work for that, right? And so it just makes things difficult. So if we consider the spring force as internal to the system, like we did with gravity here, for example, then now we can actually calculate for US. We have kinetic as well that we can calculate for, right? And assuming there's no friction, we can just say, okay, well, it's an isolated system, W equals 0, delta E, that's equal to US, right, plus K. Well, then you might be thinking, okay, well, then what about UG, for example? Well, if the distance is along this way, right, and the force of gravity is like this, that's a 90-degree angle. It'd be doing 0 work in that case. And at the same time, if you were to say, okay, well, what if I want to internalize gravity, right? What if I internalize it? Well, if you're moving along a horizontal axis, right, you're not changing your height. So change in height is 0, so it doesn't matter really because delta U is going to be 0, right? There's no change in gravitational potential energy in that case. Now, an object sliding along a surface with friction, if you want to externalize friction, like I said, you say work is equal to delta E. If you externalize it, that's equal to K plus U. If you internalize it, we say, okay, then it's an isolated system. Work is equal to 0. There are no other external forces. That's equal to delta E, and that's equal to K plus U plus E thermal. So block and the surface interact via kinetic friction, but these forces are internal to the system. There are no external forces to do work, so the system is isolated. So friction can be in the system where work due to friction is 0, so it's an isolated system, and then thermal energy is what we calculate for on the right-hand side, right? Or friction can be outside the system where there is work due to friction, and then your delta E theta is equal to 0. E thermal, my bad, not E theta, E thermal, right? So that's kind of a repeat of what I said there as well. Now, here's another good example that we can calculate for. Let's see if there are any other. There's a couple more examples here with, I'll go over these two as well, and then I'll probably, I don't know if I should move on to the online homework after that, or there's some earlier things here, but I think just let me know, like right now, real quick in the chat or whatever. Do you guys have a problem just out and out calculating energy? Like half mv squared, half kx squared, mgh versus mg, hf, hi, right? Do you have problems calculating energy and like understanding the concept of how to calculate energy? Or are you guys good with that? Mm-hmm. Yeah, that's an excellent question. It'll depend on your understanding of what's going on in the specific situation. So if I'll just write here honestly. If I am at the top of the cliff right here, right? And here's the bottom of the cliff, right? If I start at the bottom of the slope here and I make this my 0 point, if I think about gravitational potential energy being mgh, what is my h here? Well, it'd be 0, right? Because I made this point right here 0, right? This is my arbitrary 0 point. If the bottom of the cliff is 0 and the top of the cliff, let's say, is 20 meters, right? Then h is 0 here, right? So if h is 0, then your gravitational potential energy at the bottom is 0. But if you're at the top of the hill now, right, then UG is equal to MGH. Now you have a height of 20 meters, and so then you have gravitational potential energy, right? Same thing if you were here at the middle, right? If you were at 10 meters up at the top, then you can calculate MGH, but H would be 10 in that case, for example, right? So if there's an increase in height, right, if you have a height at all, so it just depends on where you set your 0 point as well. If you set your 0 point at the bottom of the cliff, then you would have a zero gravitational potential energy, right? So gravitational potential energy, its presence, right, or lack thereof, is dependent on your height. Now, kinetic energy, presence or lack thereof, is dependent on if you're moving or not. If you're moving, you have a speed, right? So you have a gravitational, or have a kinetic energy. If you're not moving, if you start from rest, for example, then maybe your initial kinetic energy is zero, because if kinetic energy is equal to half mv squared, if v is equal to zero, then kinetic energy is equal to zero. So it just kind of depends on how you read the equation, what's going on. If they're moving, right, initially, there's initial kinetic energy. If they're also moving at the end, if they want you to figure out like final speed or something, they're going to also have final kinetic energy. If you start from at the bottom of the cliff, for example, right, if you set that as your 0 point, then you have zero gravitational potential energy. So any deviation from that 0 point, if you move upwards or move downwards, then you're going to have a different gravitational potential energy. So, for example, right, if that cliff problem, once again, if you make here the middle your 0 point, right, and let's say here at the top is 10 meters, and this is 10 meters at the bottom, right, then if you were to calculate your gravitational potential energy, at the top it would be mgh, and that would be 10 meters, right? And then at the bottom, it would be mg, and then h would be negative 10 meters, relative to this arbitrary 0 point. So it just depends on where you set your 0 point at to figure out, what your gravitational potential energy is. Because if you move downwards, you just decreased in gravitational potential energy. If you move upwards from this middle point right here, you increased. Otherwise, if you make the bottom your 0 point, then anytime you move upwards, you're going to increase in your mgh. Because you go from 10 to 20 to 30 to 40 meters, for example. And so your h keeps increasing, so your ug keeps increasing. But yeah. Yeah, and I mean, please, just let me know in the chat right now, or use your mic. Do you guys have any problems, calculating for energy stuff? Or, because I'm going to focus really on these last couple problems, because these are most complex types of problems, and that's what you're going to see most likely on the quiz tomorrow and on the exam. Because otherwise, this stuff right here, I feel like it's mostly plug and chug. And what was I going to say? Mostly plug and chug. And there's a lot of practice on the online. And I'll be at the MSLC tomorrow as well to reinforce any of these really basic work concepts. Because it just matters, calculating for work here just matters on the angle, the force, and the distance. So it's not too horrible. But the rest of this stuff here is where it gets really difficult to understand the complex types of problems. So, I mean, I don't know, you guys aren't really talkative today, so I'll just keep chugging along, I guess. So, here's another problem about speed at the bottom of a water slide. While at the county fair, Katie tries the water slide. She says the starting point is 9 meters above the ground, right? Starting point is at 9 meters above the ground, so that's our HI, for example. She pushes off with an initial speed of 2 meters per second, so that's our VI, 2 meters per second. And the slide is very slick and can be considered frictionless, so there's no friction in this case, right? Slide ends, followed by a horizontal portion where the coefficient of friction is 0.40, right? So part A is asking us how fast will she be traveling at the end of the slide before the horizontal portion. So if this is the slide, right? If there's it's like this, basically. This is our slide, right? Here's the horizontal portion. Here's basically the bottom of the slide, right? So they want us to figure out how fast she'll be traveling at this point right here, right? So let's look at what forces we have in question. Can we internalize any of them? Do we have to externalize any of them, right? Is it an isolated system? Is it not an isolated system? Stuff like that. So she's at a starting point 9 meters above the ground. What does that indicate? Exactly, right? We have some specific height that they gave us. We're starting at a specific height. So there's a potential to move. MGH, right? H is 9 in this case, right? Now, for that mgh, that's equal to ug, right? It's better to internalize gravity in that case, right? Because then it's just easy to calculate what's the difference between her initial height and her final height. So we internalize, right? We internalize gravity so we can calculate for delta ug, right? Now, we also internalize for kinetic energy, right? We want to figure out what the speed is at the bottom of the slide. Now, there's no friction, right? Friction is not present. So friction doesn't do any work. Work is 0 due to friction. And at the same time, there's no thermal energy, right? So internalizing or externalizing friction doesn't matter because there's no friction, right? So is this situation an isolated system or not? Do we have any external forces acting on the system? No. Excellent, right? So if it's an isolated system, work is equal to 0. That's equal to the change in energy. And that's equal to change in kinetic plus change in gravitational potential energy, right? And like I said, it's probably easier to forget the delta K plus delta UG stuff and just do EF minus EI is equal to 0, and then EF is equal to EI, right? Oops, I put EI, my bad. So if that's the case, and this is an isolated system, we look at what are our initial energies and how are they equal to our final energies, right? And in this case, energy is fully conserved. There's no energy added to the system due to work, and no energy removed from the system due to the work. Energy is fully conserved, also in the perspective of the equation. And so what is our initial energy for potential energy, right? We want to look at that. So we know it's mgh, right? Hi. She started off at 9 meters, and there's 10 meters per second squared due to gravity. But we don't know her mass, right? So we can just say 90 m for the moment. Now for initial kinetic energy, it says she's pushed off with an initial speed of 2 meters per second. So our VI is 2 meters per second. So we can say, okay, half times her mass, still unknown, VI, that's 2 meters per second, and then we square it. Now our final gravitational potential energy here is what she is at the bottom of the slide, right? So we said this was the bottom of the slide here, right? Here's the horizontal portion. At the bottom of the slide, it would be 0. Why is it 0? Yep, exactly. mgh, f. If h is 0 at the bottom of the slide, right, then that whole gravitational potential energy goes to 0. So this is 0. How about kf? Half mvf squared. Well, that's what we're trying to figure out, right? So we're trying to figure out what this vf is. What's her speed at the bottom, right? So we have 90 m, half m4 basically, right? And this half m4, because this is 2 squared, so this before half m4, well, that's just 2m, right? So 90m plus 2m gives you 92m. And then you can see m's cancel out, and you can easily multiply the 2 over, take the square root, and figure out what your VF is, right? So that's not too bad. So initial versus final, you can think of initial versus final positions. What is my initial energy as the first position? What's my final energy at my final position, right? So my initial position, I was at a height of 9 meters. My final position, I was at the bottom. If they were to ask you, okay, what's the speed at the midpoint of the slide, right? Medium height or mid height, you can say maybe at 4.5 meters. So we can start off at 9 meters initially, right? mgh, mg times 9, or m times 10 meters per second squared times 9 meters. That's 90m. And then our final height, instead of being at the bottom where it's 0h, we can say mg times 4.5. 4.5 times 10, that's 45, right? So 45m in this case, we want to figure out. So it's just a matter of looking at what's your initial, final positions, what is the energy at that initial position, what's the energies at the final position, right? So that's the idea there. Now, let's say for part B now, saying how far will she travel horizontally before friction brings her to a stop? Because remember, there's that horizontal portion where the coefficient of friction is 0.4, right? So for that friction part right here, well, there might be 2 ways of thinking about it. Because remember, I said earlier that you can either externalize or internalize friction, right? If we internalize friction, we can say that, okay, if we internalize it, work is equal to 0. It's an isolated system. Delta E, this is equal to K plus U plus E thermal. Oops, E thermal. My bad. Plus E thermal, right? And so the other way is if you could consider that it's external, so you can say W is equal to delta E, and that's equal to delta K plus delta U, right? That's another way of putting it as well. Now, I think it's just a little bit simpler maybe to go with the thermal energy route as opposed to the external work route, right? So if we set everything to be internal, so work is equal to 0, delta E, that's equal to K plus U plus E thermal, right? Then we can say that work is equal to 0, equal to delta E, so work is equal to EF minus EI, that's equal to 0, so EF is equal to EI, right? We look at what our initial energy is. So for initial energy, it's going to be made up of some kinetic, right? And some potential energy initially. And that's at the bottom of the slide, remember. So, it says slide is very slick. Okay. All right. So, I think, I don't know if I messed this one up or if I... Okay, let me read this real quick again. The only thing I'm concerned about here is the 92M. Because I think I started maybe from the very top instead of like at the bottom of the slide instead. All right, let me look at here. What do they have here for it? So I'm making sure that I'm getting all this right. Okay. Okay, what about, alrighty, let's see if we did work is equal to 0, right, is equal to delta E, so it's EF minus EI, right, and then that's equal to, actually, hold up, so let's do it this way. W is equal to 0 equal delta E, that's equal to delta K plus delta U plus E thermal, right? So then in that case, right, what we can do is if we just say that delta K plus delta U plus E thermal is equal to 0, right? Then your KF minus KI, right, plus UF minus UI plus the thermal energy there is equal to 0, right? So in that case, you can add over KF plus UF is equal to, plus thermal energy as well, is equal to UI plus KI, if you add things over like that. So, for U initial and U final, actually, for U initial and U final, if we're starting from the bottom of the slide, right, this is the bottom of the slide here, if this is our initial point and our final point is like after the rough patch, do we see any change in our gravitational potential energy? Or are we at the same height? Same height, right? So final should be equal to initial. These two would cancel out. So you're left with Kf plus E thermal is equal to Ki, right? So for that, we want to figure out hold up. I don't know what I'm messing up here. Kf plus thermal energy. Okay. Because what this would require is half mvf squared plus the thermal energy that we can figure out. That would just be the work due to friction. And then this is half mvi squared. What we ended up initially, our initial would be at the bottom of the slide, and our final would be after the rough patch. And so our initial at the bottom of the slide would actually be our final from the first part, which is the 13.56 meters per second. So we would just need the speed after the rough patch, what you end up with. And so, oh, I'm stupid. That's why I was confused, because I misread this part. Before friction brings her to a stop. So our final after that rough patch should be 0. Our final after that rough patch would be 0. Because half mvf squared, that's what I was missing, sorry about that. Vf would be 0, because she's brought to a stop after the rough patch, right? So Kf would be 0 as well. And so then you're left with E thermal is equal to your initial kinetic energy, right? And so for your initial kinetic energy, right, that was equal to half m and then vi squared, right? That was 13.53 meters per second squared, right? Because our initial is at the bottom of the slide, and we determined that the speed at the bottom of the slide was 13.56 meters, 56, not 53. So that's our initial meters per second, right? 13.56 meters per second, and then we square that, and that's equal to our thermal energy. So our thermal energy we can actually calculate. Remember I said, regardless if you make friction external or internal, it just depends on essentially what side of the equation you have it on. So you can still calculate for thermal energy here as the work done by friction. So you do force of friction times the distance at which it's applied, and then the angle. So obviously if you're moving this way, friction acts in the exact opposite direction. So there's a 180 degree angle. So it acts exactly opposite to it. So that gives you cosine 180, and that's -1. Then you have your mu from earlier, that's 0.4. So negative 0.4 times your gravity, which is 10. So that gives you -4, right? So you get -4 when you multiply u times g. -4, and you don't know the mass, right? And you don't know the distance. That's what you're trying to figure out, right? So then you do half m times that speed that we had, right? That was our initial speed. And that's equal to -4md, right? And then for that part there, you would just set everything equal to, so we do half m, 13.56 meters per second, and you square it, and that's equal to your -4md. You divide over the 4, or you divide over the mass, my bad, those cancel out. And then you can solve for your distance, but then for your negative here, so I think the issue here with the negative Might just be due to the fact that they wanted us to calculate g as negative 10 meters per second squared, so that'll cancel out the negative sign there. And yeah, I mean, anyway, I think that's how you would be able to get that done. I think they might, what mistake I might have made is that I guess when you're doing work, so my bad. Okay, so I'm stupid. I forget what I said about the gravity part. When you're calculating work, I forgot about this part, is that you have to take the absolute value of the force. So, everything just becomes absolute value in the end for this part. And so they have mu times absolute value of Fn, right? Negative done by friction will move all the kinetic energy. Yep. So you would just honestly just cancel out this negative sign here, and then that's how you can figure out what the distance traveled is. And so if you do that, let me calculate just to be sure that everything makes sense there. So cancel out the m's. Yep, yeah, 22.98 is what I got, so that's about 23. Yep, so that's the way to do it for that problem. That one, I just messed up the final kinetic friction there for some reason, overlooked it. But you can see that, once again, this is a lot of math stuff and whatnot, so, but generally you follow the same rules. So the only example left here would be this gravity in the spring, and there's power as well. Power isn't bad because it's the change in energy over change in time, and I'll go over that here in a second. But I don't know if we'll have time to go over the online homework stuff. Damn. All right. I think it's just important to go over these examples, though. That's most important. The online stuff wasn't, terrible. At least I didn't get a lot of messages about the online. But, yeah. This example says Nina sprints and lands on a bobsled that is at the top of a slide at a height of 6 meters above the ground. So we have our height here is 6 meters. Right? And initial at the top of the slide is 10 meters per second. So initial speed is 10 meters per second. Nina and the bobsled total mass is 60 kilograms, so their mass is 60 kilograms. And they slide down the ramp and slam into a spring that has a spring constant of 4,000 newtons per meter. Ignore friction for this problem. Okay, cool. So if we're ignoring friction, there are no external forces here. We're internalizing gravity, right? We're going to be internalizing gravitational potential energy and all that, and kinetic energy as well. And there's no friction, so there's no thermal energy, there's no work done by friction, anything like that. So this is an isolated system. Work is equal to energy is equal to 0, right? So we have EF is equal to EI again, right? They want us to find out what's Nina's velocity when she reaches the bottom of the ramp before she hits the spring, right? So there's final energy involved and there's initial energy involved. At the bottom of the ramp here, right, her final gravitational potential energy should be 0 because she's at the bottom of the ramp, and we can set that as our arbitrary 0.0 meter height. So if height is 0, then UF is 0 at that bottom of the ramp. For our final kinetic energy, right, it should be half mvf squared. Vf is what we're trying to figure out, which is the speed that she reaches at the bottom of the ramp. And then our initial potential energy would be mgh, so her mass, right, at 60 kilograms, times gravity 10 meters per second squared, times her initial height, which is at 10 meters, or at 6 meters, 6 meters above the ground, right? So we take 60 kilograms times 10 times 6 meters above the ground. That gives us our mghi. And then for kinetic energy, initial, she was moving initially with 10 meters per second. And so we can do half mvi squared, right? You can add these two together and then solve for Vf, right? It's not too bad. The issue here is when we get to the spring part. So how much does the spring get compressed when it's fully stopping in the sled? What does it mean? This is what I missed earlier. What does it mean when it fully stops? It means that your Vf should be 0, right? So our final position should be 0, or our final speed should be 0, right? And so, once again, we are going to be internalizing spring force because spring force is not constant. We want to keep things easy to calculate, right? So this is still an isolated system. W equals 0 equals delta E. In this case, we only factor in kinetic energy and spring potential. The reason why is we can still technically calculate mgh. We can still calculate gravitational potential energy. But why do we consider it to be 0 along this horizontal point here? Why is ug 0? Any ideas along this point here? Why would our gravitational potential energy be 0? So we do have kinetic energy, right? We're moving. We have movement, so there is kinetic energy. But for gravitational potential energy, delta UG, why is that 0? Yeah, because we can have our arbitrary point here at the bottom of the ramp. This is at a height equal to 0. So from here to here, your height didn't change. For both points, height is 0, right? So MGHF, MGHI, right? Whether we're here or here at the spring, in both cases, H is 0 because you're at that 0 point for the height. So that's why we don't even, it's just easier to leave it out. So in this case, for your work, since it's an isolated system, work equals 0 is equal to delta E. We can say, okay, well, EF minus EI is equal to 0. You have EF is equal to EI, right? What's our final and initial energies? So for final energies, right, for final and initial energies, our final, we're going to have maybe some kinetic and some spring potential. And initial, some kinetic, some spring potential, theoretically, right? Oops, UI, say UI, right? Now, do we have actually any initial potential, spring potential energy? At the beginning, at the bottom of the slide here? Do we have any spring potential energy at the bottom of the slide here, at the beginning, at our initial point? Yeah, before it touches the spring. So initially, like here at the bottom here, this would be I and this would be F pretty much. So before touching, is there any initial spring potential energy? So we'll think about what spring potential energy is equal to though, right? Because it's equal to half kx squared. So our x, exactly, right? So there wouldn't be any spring potential energy initially because you haven't compressed it. You haven't given it any displacement. So there's no initial spring potential energy. So this would be 0. Is there initial kinetic? At this point? I mean, probably, right? Yeah, I mean, it's moving, so there should be there should be some kinetic energy, right, initially. So this is 0, right? There's no displacement yet to the spring, and the kinetic energy initial, there should be a value for that. That would be half mvi squared. And then for final spring potential, we should see half kxf squared. What's the final compression distance? right? And for final kinetic, is there a final kinetic? Do we have any final kinetic energy? Exactly, right? So final kinetic energy could be 0 because your VF would be 0. So then you're just literally just solving for half kxf squared is equal to half mvi squared. You already figured out this, the speed at the bottom. Your VF from part A is your VI for part B, right? So you take your, what was that, 14.8 meters per second, square it, right? Times your mass, which was the 60 kilograms, divide by 2, and you have your spring constant, that was 4,000 newtons per meter, and then you can solve simply for your x, and that's how you can get your 1.8 meters. That's not too bad. It's just separating different points. You calculate what your speed is going to be at the bottom of the slide, right? You can do that using kinetic and gravitational potential energy changes. And then from that, since you no longer have any change in gravitational potential energy since you're at the same height, then you can figure out, okay, well then how does my kinetic energy change and get transferred into spring potential energy? So, and once again, since it's an isolated system, everything's conserved. Whatever decrease you see in kinetic energy, right? Because kinetic energy is going to go down to 0 basically for that final, because it stops. Whatever decrease in kinetic energy, you're going to see a subsequent equal increase in spring potential energy, right? Now, when it comes to power, power is, like I said, transfer of energy over time, right? Rate at which energy is transformed or transferred. And that's measured in joules per second. Energy is in joules, time is in seconds, and that's equal to a watt as well. So for power, you can say, well, if energy is equal to work, then work is FD cosine theta divided by time. So you can also write power as FV cosine theta, right? And the reason why is that x over t is equal to your speed, right? So you can also write it as FV cosine theta. So rate at which force transfer energy is the output power. If a constant force acts on an object moving with a constant velocity at an angle theta to the direction of v, then this is your output power here. And these are really simple, honestly. Like, you just take your change in energy divided by time. So if you have a time interval of 0.45 seconds, that's your time. And then let's see here, it says what power output is required to compress a spring with a spring constant of 5 kilonewtons per meter initially at its equilibrium length. So if you're initially at equilibrium length, your I, your half kxi squared, your ui is 0, and your f, well, your final distance, right, compressed at 6 centimeters. So you do 0.06 meters, square it, times your spring constant, and then divide by your time to get your power. That's not too bad, right? Same thing here, like just this is more conceptual, right? You're just looking at change in energy over change in time. Well, to maximize it, right, because you're changing in your gravitational potential energy here, you want to make your numerator as big as, there we go. You make your numerator as big as possible and your denominator as small as possible, right? So we want to have the greatest change in gravitational potential energy with the smallest time as we could, right? So you just look at mgh, right, the change in gravitational potential energy, divided by your time, right? But yeah, I think this might be a typo on this one because I think they forgot to give you the heights for these. Oh, actually, never mind. They got 10 meters right here. I overlooked it. So you just go ahead and like calculate each one. What's the MGH for this one? What's the MGH for that one? This one, right? Divide by your times for each and compare the power for each one. And this is, once again, just another practice problem with power output. But that's the brunt of like the really difficult problems that you have to do for energy, and hopefully that cleared some things up with regards to how to internalize and externalize gravity and forces and stuff like that. Hopefully the rest of, I know they did a lot, but I mean we went over how to calculate work again, basically FD cosine theta, right? We described so many times gravitational potential energy, what it is, how to calculate kinetic energy. I'm assuming by now like the actual calculation of energies themselves and like the concept of what kinetic energy is, the concept of what potential energy is, shouldn't be too bad right now. But hopefully doing some of these extra practice problems, seeing how they work, right, getting experience with them, helps you understand a little bit better of what's going on. But I think that's probably about it. Let's see if we can get maybe like 1 or 2 online homework problems in real quick. Is there anyone that you guys had in mind that you guys want to go over real quick for the online? This is the online. Yep. Yeah, sure. What do you need to go over the written? Part C? Yep. So the spring at the end of the track eventually stops the roller coaster, and the spring gets compressed in amount delta L. So this is really simple, actually, like not simple, similar to the problem that we just did with the spring at the bottom of the slide, right? So with this one, you have an initial and final energy, right? Your initial energy is at the bottom here, right, at the bottom of the loop, and your final energy is when it touches the spring, right? So your final energy, if we want to look at, once again, this is going to be internalizing everything, so we don't want to see any external forces. So if we were to have EI is equal to EF, right? You have an initial kinetic, you have an initial gravitational, or what's it called? The spring potential. You don't have initial gravitational because from here to here, you're not changing your height, right? Your height stays the same. So there's not really a change in gravitational potential energy. So there's no reason to include it really. Now, with that being said, you will have, for your energy initial and final, you have kinetic initial, spring potential initial, and then kinetic final and spring potential final, right? For final kinetic, this should be 0 because the roller coaster comes to a stop once it hits the spring, right? And then for initial, right, the spring is at its equilibrium position, right? That's what Eric said earlier. So if it's at its initial equilibrium position, then there's no displacement, so x is equal to 0. So this goes to 0 as well. So what you're left with is that your initial kinetic is equal to your spring final, right? So initial kinetic is at the bottom here. So we want to figure out what's our kinetic energy at the bottom here, right? So for kinetic energy at the bottom, the way we can figure it out is by looking at how or what change did we observe from our very, very first initial energy here. So we went from having mgh, right? This is at a height of what, 45 meters was it? So there's a mass of the roller coaster that was 1,500 kilograms. There's a acceleration due to gravity 10 meters per second squared, and there's a height of 45 meters, right? So that was our initial. At the bottom of the loop here, which is what we're trying to get at, so we can travel along this horizontal distance, at the bottom of the loop here, all of our energy goes from potential to kinetic, right? Because we went from a height of 45 all the way to a height of 0 at the bottom here, right? So whatever decrease we saw in gravitational potential energy, we saw an increase in kinetic energy of the same amount. So if we're trying to figure out what the kinetic energy is at the bottom, it's a matter of figuring out what was the change in gravitational from the top to the bottom. Because whatever decrease we saw from top to bottom in gravitational potential energy, it's the same increase that we see for kinetic. So that's why I calculated for the change in gravitational potential energy here, right? You can see that your EI is equal to EF, right? So if you're initially, you only had potential at the top, right? That was mgh. Oh, I, my bad, right? Plus ki is 0 because you're not moving at the top. And then EF, mghf, well, you're at the bottom, so h is 0, and that equals your kf, right? Your final speed at the bottom of the loop. So in reality, if these are both 0, then your initial gravitational potential energy is equal to your final kinetic energy. That's what I said earlier, because like whatever initial energy you had, right? Because energy is conserved in this case, it's an isolated system. Whatever decrease in gravitational potential energy is going to see the same increase in kinetic, right? So if we started off with 300,000 joules or whatever it was, you're going to end up with 300,000 joules, same 300,000 joules, just kinetic now instead of potential, right? So we calculate now, we do mg hi, right? Forget the whole negative sign stuff here. Just remember what I said earlier about the mg hi is equal to kf, right? So you just take your 1,500 kilograms times 10 meters per second squared times your initial height. That was 45 meters, and that gives you your final kinetic energy at the bottom. And that should be a positive 675,000 joules. Once you have this kinetic energy at the bottom, right, that's technically your initial kinetic energy from here to here, right? So here's your initial along that horizontal portion, and here's your final along the horizontal portion. So, once again, going back to EI is equal to EF, right? Here's your initial kinetic energy, here's your initial spring. Here's your final kinetic energy, here's your final spring. Remember we said earlier, initial spring potential energy is 0 because there's no displacement of the spring. The roller coaster hasn't touched it yet, so this is 0. And our final kinetic energy is 0 as well because by the time you touch the spring, the roller coaster will have stopped. So there's no speed anymore. Half mvf squared, vf is 0. So this goes to 0. So then you're just left with whatever kinetic energy you had at the bottom of the loop gets all converted into the final spring potential energy, right? So you set 675,000 joules equal to half kxf squared. What was your, that's how you can figure out your final displacement. Does that make sense? There you go. Sound good, Matthew? Okay. Mm-hmm. Yep. Yep. And that's I think you said gravitational potential energy. I think you might have meant spring potential energy. Yep. But hopefully that makes sense, guys, overall about like initial versus final positions, and stuff like that, and internalization versus externalization. Do you guys think that made sense throughout the session, or are you still confused? Or is it at least like sort of kind of making sense a little bit more now? Okay. All right. Well, if it is making sense, then that's great. I do have a session tomorrow from, what is it, like 10:15-ish to 12:15. Not, well, officially from 10:15-ish to 12:15, but then I'll probably be there for the students in the Zhang section, just open, kind of chilling in the MSLC till like 3 or so. That's when you guys have your lectures, I believe. So if you guys have any questions during that point, or if you're in Ansari section or your Ordinova section, feel free to stop by if you're on campus and ask any questions, shoot any questions, anything that I didn't cover, and then, yeah. But we went slightly over time for this session, so I'll probably end it on this note. And I'll run the recording here, and it should be uploaded by the end of the night for sure. Alrighty. So I'm going to stop the recording now, and hopefully for those who attend this session and for everyone online, you guys benefit from this.